Hello world and internet. Welcome back to Boolean Maths. Today we're going to be talking about solving nonlinear inequalities. So let's get to it. Okay. So there's two approaches to solving a nonlinear inequality. And what I mean by nonlinear inequality would be something that's like, linear would be like 2x minus 3 is greater than 7, right? I'll just write that out real quick. So 2x minus 3 is greater than 7. That's a linear inequality. You just solve it like you'd solve a linear equation. You'd add 3 to both sides, divide both sides by 2, blah, blah, blah. A nonlinear inequality is something like a quadratic or some sort of polynomial or a rational function or anything really. You could do the sine of x, whatever. So there's two primary approaches. If we're doing something that's polynomial or rational, which is what we're going to focus on today, you could do that either algebraically or graphically. So we're going to do both for each. Typically, if you have a calculator in tow and you're not taking a test, after you algebraically solve an inequality, it's not a bad idea to break out your calculator and know how to do it graphically as well. So let's do it. All right, so example 1. We are being asked to solve this inequality. We have 2x cubed minus 3x squared minus 32x is greater than negative 48. I want to know when the left side is greater than negative 48. Okay, so unlike with linear inequalities where you solve like by moving constants to one side and variable expressions to the other, we actually bring everything to the left side of the equation. So and then we're going to plug into a graphing calculator like Desmos or something, just this part. Okay, make that bigger. So now we're comparing an algebraic expression that we could think of as a function, and we want to know when is this function greater than 0. So now I've plugged this into Desmos. Again, a graphing calculator that's online is usually a little bit better than a TI-80, whatever. So here's a graph of 2x cubed minus 3x squared minus 32x plus 48. And we want to know when is this function greater than 0. So this is probably familiar to you because you may have used this number line approach. So what we're going to do is actually, we're going to look at the graph, and I want to know when it's strictly positive. So using my highlighter here, I'm just going to highlight the parts of the graph that are positive. When I say it's positive, when is y positive? The y values in the function. And here, everywhere else it's either 0 or negative. It's even worth putting like an open circle on those zeros. So let's talk about those zeros for a second. The zeros in a function are sort of neutral values. They're neither positive or negative. And the reason we care so much about zeros is that they are opportunities for your function to change from positive to negative. So I'm going to just make a little number line here, and let's state those opportunities on the number line. That left arrowhead is beautiful. All right, so here's 1, 2, 3. So we have negative 4 is one of the x-intercepts, 1.5, and 4. Now, if you look at the original inequality, you have a strict greater than. So what we want to do is we want to put open circles on all of those zeros because we don't want to include them. Now, we're curious, where is the function positive? So you can see here, just from looking at the graph, the green highlighted regions, that we're positive from 4 to 1.5 and, negative 4 to 1.5 and 4 to infinity. And it's just for fun, we can just put a little positive here, positive there, maybe a little ring around it, and that's just reminding us those are the two places. So this is the solution to that inequality. All values between negative 4 and 1.5, non-inclusive. So we're going to use interval notation, negative 4 to 1.5, and that's one set of values that would satisfy the inequality. And then also the other set would be 4 to infinity. Wonderful. Now, so that is definitively the answer. Let's go over here. Now the algebraic solution is starting the same way. We move everything to the left side of the equation and we're comparing the function to 0, right? So we're like, where is it above 0? Where is it below 0? So once again, same exact problem, but we don't have access to a graph. So what we want to do is you would factor it. Again, you learned how to factor polynomials. So you do whatever method that you would employ to, synthetic division, yada, yada, to get your factors. So once you get the factors, then you can figure out the zeros. Once again, we're going to make a nice little number line. And we're going to state the zeros that we just found on that number line. We have -4. We must put them in order, obviously. And then we have 3/2 and +4. So this is x equals 3/2, x equals -4, and x equals 4. That's where we are getting our zeros. Open circles on the number line just to remind us that we're looking for a strict inequality. We only want to know when it's positive. So if you notice, when I graph this in Desmos, just come over here, I actually call the function f of x, right? So I want to know, when is f of x greater than 0, right? So you can think of this function also as f of x. So we want to know, when is f of x greater than 0? Well, because x-intercepts are opportunities for the function to go from being positive to negative, right? It has to cross through. If you're above the x-axis and then you're below the x-axis and it's a continuous graph, it must go through 0 to become negative, right? So, but once it crosses over at a 0, right, it stays positive or it stays negative until that next opportunity. It's kind of like an exit on a highway or something like that. Once you exit, then you're off the highway until the next opportunity to get back on, or yada yada. Okay. Now, so I want to just pick some test values from each interval to see if the function's positive or negative. So anything to the left of -4, I'm going to plug in -5, something between -4 and 3/2, or as we know, 1.5 would be, I think that would be wise to just plug in 0. A value between 1.5 and 4, let's just do f of 2, and then something to the right of 4 is that. So if I plug in -5 to the function, I'm going to get, okay, so as promised, I evaluated f of -5, f of 0, f of 2, and f of 5. So you see that f of -5 is -117. So I can put a negative value for all values to the left of -4. We're going to be negative. So between -4 and 3/2, or 1.5, we know that f of 0 is a positive number. That means this entire interval has to be positive, because once you cross into the interval from -4 to 1.5, once you just test any value in there, if you see a positive value, it means the entire interval must be positive until the next opportunity at 1.5. And then when you plug in 2, you see that the graph goes negative, so it's negative there. We don't want it to be negative, so I'm not going to highlight that. I'm just going to point out that we have a negative value there. And then once we transition to 4, we're at 0. Something to the right of 4 is f of 5, and that's 63. It's positive again, so you would highlight that. And then you see that, sorry, I should probably write infinities on my number line. That's our solution. So, and because they're open circles, you would just write interval notation, -4 to 1.5 union 4 to infinity. All right, so there's that. So it looks like we got the exact same answer that we had over here with the graphing solution. Again, just to reiterate the importance of zeros, when you look at the function here, you can see that -4, 1.5, and 4 are very significant values. And as I mentioned in our kind of imaginary exploration over there when we were trying to envision the graph, when you cross here, once it's positive, it stays positive all the way down to here. Likewise, Once it crosses negative, it stays negative up until its next opportunity to change, when it becomes positive again. All right. I don't know if you all can hear the thunder outside, but it's kind of ominous. I think that the weather gods know that math is happening here, and they're not happy. All right, next we're gonna solve a rational inequality. So now again, if you kind of know how to do this, you might want to pause the video. I always say this and try it on your own. But here we go. So we have this rational function, 2x minus 7 over x minus 5 is less than or equal to 3. Trying to compare that left side of the equation, even if you saw it in your mind as the left side as a function and the right side as a function, trying to figure out where the graph is underneath the line y equals 3, that's that's going to be a tough one to envision. So it's much easier to take that 3 and bring it to the other side. Now we're comparing an algebraic expression to 0, because we can easily, or not always easily, but in a much easier way, envision the proper values for a function that would satisfy an inequality when you're comparing to 0, that neutral value. So all right. Here we go. We're going to focus on the graphing solution again. So I'll move the 3 over. So we want to look at when is the function 2x minus 7 over x minus 5 minus 3 less than or equal to 0, right? So I'm actually seeing this whole entire function right here. I'm calling it g of x. So I want to know, when is g of x less than or equal to 0? So we called it g of x here, right? And I graphed it. So when you look, the only places, well, actually there's quite a few, we're less than or equal to 0, strictly less than here, and we're less than over here, but also including 0, okay? Because we want to know when it's less than or equal to 0. So so you have that going on. The other thing to note is this is a rational function, and you know that x cannot be, I can't hear you, but I think you said can't be 5. So maybe we should just put a little asymptote there. We know that since x can't be 5, and you see that kind of behavior on the graph, there's our vertical asymptote. So that's a barrier, and that's another type of opportunity for change. Notice on the left side of the asymptote, you have negative values, and then on the right side of the asymptote, you have positive values. So those vertical asymptotes are significant values, and those are opportunities for change when you make a number line. So there you go. So we're looking at the graph. We see where it's negative. We see the transition values. Those transitions values happen at the vertical asymptote and at the x-intercept. There's only one x-intercept. So some of you might be wondering, like, hey, why aren't we scrolling all the way to the left? Maybe it crosses one more time. How do you know that that's the only 0? Because I didn't solve for that 0 using algebra. I'm trusting the graph. I did pan out and I looked. The other thing that I do know is, actually I don't know yet. I was about to say I know the horizontal asymptote. We don't know the horizontal asymptote from this. So I do feel a little bit vulnerable using this technique without manipulating that algebraic expression more. However, I did pan out and I did look, and it does appear that there's it looks like there's a horizontal asymptote at like y equals -1 or something like that. I did copy and paste this graph in here, so it's not dynamic. I can't go and look at it right now. Just I wanted to be able to mark it up. But anyway, but you can trust me that it doesn't cross the x-intercept. It doesn't cross the x-axis again. We're going to be negative forever. So let's make our number line here. Whoa, that's an awesome arrowhead. I should win a prize for that one. Ooh, look at that one. Okay. We have 5 and 8. Now I'm going to put an open circle at 5, and I'm going to put a solid circle at 8, because 5 doesn't represent a place where the function equals 0. It's just the place where the function switches from being negative to positive. So it's an opportunity for change. It's a 0 of the denominator, if you will. But the x-intercept at 8, 0 is a legitimate value. When I plug in 8, the function gives me back 0, so that satisfies the inequality, because I also want to know when it's equal to 0. So that gets a solid dot, and then you just look and you see, okay, well, it looks like we're negative to the left. I mean, sorry, yeah, that's correct. Negative to the left of 5, and we're negative to the right of 8. So, and that's it. We're only looking for negative values. We don't want to know when it's positive. So we'd write our interval notation here. We're going to say negative infinity. I should probably write negative infinity and positive infinity on my number line. Sorry about that, guys. So negative infinity to 5, union 8 to infinity, and that's it. Done and done. So that's one answer. Let's see what happens when we solve this algebraically. So algebraically, we'd want to focus, again, on moving everything to the left side, and then what we want to do is condense this into one expression. You have that -3 there. We want to make this one rational expression and factor it as much as possible. So the way we would do that is we can start by multiplying top and bottom of the 3 by x minus 5. X minus 5, we have a common denominator, so we have 2x minus 7 minus 3 times the quantity x minus 5 all over x minus 5 is less than or equal to 0. And then distribute that -3. Notice I used parentheses, and I'm really emphasizing that you're distributing a -3. So you have 2x minus 7 minus 3x plus 15 all over x minus 5 is less than or equal to 0. Combine like terms, and you get -x, and then plus 8 over x minus 5 is less than or, is less than or equal to 0. So there you have it. Well, we don't have it, we're not done yet, but it looks a lot less intimidating if you know anything about rational functions. If you were to think about this again as like a g of x scenario, that left side of the equation, and you were to compare where does that function land, that is g of x, just in a more simplified form. It's the exact same function that we graphed before. Now you can see that it does have a horizontal asymptote at y equals -1 because the degree of the numerator and the denominator are the same. Leading coefficient ratio is our end behavior, or horizontal asymptote. But the thing is, the trick to doing these is making a number line, and yeah, that's funny. And we have negative infinity, positive infinity, and then you're stating the zeros of the numerator and the denominator on the number line. So the zeros of the numerator are going to be -x plus 8 equals 0. That's -x equals -8. So we know that's the 0 of the numerator, which is a legitimate 0. So I'm going to put that on the number line, solid dot. And the 0 of the denominator is going to be x minus 5 is equal to 0. That means that x equals 5. So I'm going to put a 5 on the number line with an open circle. Okay. So now we have the two opportunities that this function has for changing to go above and below 0. Again, noting that even though we have a non-strict inequality where we're looking for where it equals 0, the zeros of the denominator are the excluded zeros, but there's still opportunities for that denominator to switch from positive to negative. So we put it on the number line, and we compare values to the left and right. So once again, you're just going to pick a value to the left of 5 this time. So I'm going to do g of 0, then we'll do g of 6, and then g of 9. We're just choosing one value from each interval because we know that the graph will be consistent on those chosen intervals. If it's positive, it stays positive. If it's negative, it stays negative. We want to know where it's negative. So when you plug in g of 0 to this function right here, you get 8 over -5. So that's going to equal -8/5. But all I care about is the fact that it is negative. So I'm going to shade that interval. When I plug in g of 6, that's going to equal -2, right? If I plug it, it'd be -6 plus 8 over 6 minus 5. So g of 6 equals 2, just +2. Great, because 2 over 1. That's positive. We're not looking for positive. We're looking for negative, so we move on. And then g of 9 is going to be equal to negative 9 plus 8 over 9 minus 5, which is negative 1 over 4, negative 1/4. Great, it's negative. We shade, and then we see our answer. The answer is negative infinity to 5 union 8. Now I'm thinking of a mistake I made. 8 to infinity. Over here. Oh, I did it right over there. Great. Good for me. So yeah, there it is. All right. Well, hopefully that was helpful. And if you have any suggestions, you can leave them in the comments below. Or yeah, pretty much that.